Finding absolute extrema. We say that f of c is a local maximum if f of c is greater than or equal to f of x for all x near c. Now, to illustrate that, we say that this point here, the corresponding y value, if this is your c, this is your f of c, this f of c here is an absolute maximum because for all x near c, the value of f at x equals c, this is your f of c, is greater than all f of x around this interval here. Now, we also call f of c a local minimum if f of c is less than or equal to f of x for all x near c. And to illustrate that, suppose this is our function. This point here is a local minimum, that f of c, that is the y value, because for this interval here at x equals c, f of c is the lowest, or that value is less than all other f of x on that open or on that interval. So now for the absolute maxima or minima, or absolute maximum or minimum, we say that f of c is the absolute maximum of f if for all x in the domain of f of x, f of c is greater than or equal to f of x. In other words, if you compare all your local maximum, the one with the highest value is your absolute maximum. And similarly, for the absolute minimum, f of c is called the absolute minimum if for the entire domain of f of c is the least value. That means if you're going to compare all your local extreme values, the lowest value is your absolute minimum. So an absolute maximum or absolute minimum is called an absolute extremum. Now, to give you a visual representation of absolute extremum, for this function here, since the function extends up to infinity and goes to negative infinity, there is no absolute maximum nor minimum in this function here. But at this point here, or at around x equals -2, the value for that, the corresponding value for that is 16/3. This 16/3 here is a local maximum. And at x equals 2, which also corresponds to -16/3, is a local minimum. Now, for this example here, we have a parabola that's facing downwards, and this is the graph of the function f of x equal to 4 minus x squared. Now, at this point, at around x equals 0, this point here is a local maximum. And moreover, this is the absolute maximum, because in the entire domain of your function, this is your highest point. So at x equals 0, we have a local maximum and an absolute maximum as well. Now note that the function here extends up to negative infinity. We do not know where the function ends. Therefore, we do not have a local minimum nor an absolute minimum in this case. Now, this is an example of a function where it contains an absolute minimum, but it does not have an absolute maximum. This point here at x equals 0, we have a local minimum, and at the same time, an absolute minimum. And since the function extends to positive infinity, we don't know where the function goes to, so that's why we do not have an absolute maximum nor a local maximum. The extreme value theorem gives us a guarantee for the existence of an absolute maximum and an absolute minimum on an interval. The absolute value theorem states that if a function f is continuous on the closed interval ab, then the function has both an absolute maximum and an absolute minimum on that interval. Now, this theorem guarantees an absolute maximum and an absolute minimum on an interval because in addition to local maximum or local minimum, we would also evaluate the function at the endpoints of the interval. So we're going to compare now the values of this local extremum and the endpoints of the interval. The highest value then will be the absolute maximum, and the lowest value will be the absolute minimum. So for instance, in the given function here, on the closed interval 2 to 12, we want to find the absolute extrema. Now this function will have this graph here on this closed interval 2 to 12. As you notice here, you have here a local maximum and a local minimum. But if you compare the values, including at the endpoints of the interval, this point here is the absolute minimum, and this point here is the absolute maximum. And these 2 points here are not local maximum. This is not a local minimum. This is not a local maximum. But that is the absolute maximum, and this is the absolute minimum on the closed interval, because we also consider the values of the function at the endpoints of the intervals. Now, but if you change the closed interval to 410 of that same function, notice that the graph now of the function on this closed interval here would be this part of the curve here. Now in this case here, the point, this local maximum here will now become the absolute maximum because that is now the highest point on your graph. And the point here, which is your local minimum, will now be the absolute minimum of the graph on this closed interval for 10. So this means to say that the absolute maximum or the absolute minimum could occur on either local extreme values or at the endpoints of the intervals. Now, moreover, if you change the closed interval now to 4, 8, this will now be the graph of the function. As you notice here, this point here is the absolute maximum. That is the highest point on the graph on this closed interval here. While this point here, which is at the end point of the closed interval, is the lowest point of the function. So this is the absolute minimum of this function on this closed interval for 8. Now, if you change the closed interval to 3, 11, we now have two locations for our absolute maximum. Again, when you say absolute maximum, it is the y value. It remains to be 105, but it can now be located at two different points, at x equals 5 and at x is equal to 11. 11 is at the endpoint of the interval, and at x equals 5, it is a local maximum. And similarly, the absolute minimum here will occur at two different points. It is still equal to 73, but it can now be located at two different points, at x equals 3, which is an endpoint of the interval, and at x equals 9, which is a local minimum. And so with all these examples, we say that the absolute maximum or the absolute minimum can either occur at the endpoints of the interval or at the local extreme values. This next theorem here will outline the process of finding the absolute extrema. In here, it states that the absolute extrema, if they exist, must occur at critical numbers or at endpoints. Critical numbers are the location of your local extreme values. So to find the absolute extrema on a closed interval, first, you have to make sure that the function is continuous over the closed interval AB. And then you find the critical numbers that are on that open interval AB, and then evaluate the function at the endpoints of the closed interval and at the critical numbers that you found in step 2. And then the highest value or the largest value is the absolute maximum. And the smallest value found in step 3 is the absolute minimum of f on the closed interval AB. For example, find the absolute maximum and absolute minimum of this function on the closed interval -7, 7. So as a first step, we want to make sure that the function is continuous on the closed interval AB. How do you make sure that the function is continuous in that? You get the domain of the function and make sure that this closed interval is a subset of the domain of the function. Now, since this is just a polynomial function and the domain of a polynomial function is the set of all real numbers, so therefore we say that the function is continuous on that closed interval. And then next is to find the critical numbers. So to find the critical numbers, we first get the derivatives. So find the derivative of the function f prime of x is equal to 3x squared minus 12x. So that's differentiating x cubed, and that's 3x squared, and the derivative of 6x squared is 12x. Then, after you find the derivative, you equate this to 0. The zeros of the derivative are the critical numbers. Now, to find the 0 here, we have to factor this expression here. Now, the common factor will be 3x. So if you factor out 3x, you have x here. That means if you multiply 3x and x, you should get 3x squared. And then negative 12x divided by 3x, you have minus 4. And then to check, you have negative 4 times 3x. That's negative 12x equal to 0. The next is to equate each factor to 0. So you have 3x equal to 0, or x minus 4 is equal to 0. So that is x equals 0, and this x minus 4, when it is equal to 0, that is x equals 4. So these two numbers here are the critical numbers. The next, we are going to evaluate the function at these points here and at the endpoints of the interval. So we have evaluate function. So first at the critical numbers, and then at the endpoints of the interval. And later at f at 7. So let's have at f at 0. F at 0, when x is equal to 0, we have 0 cubed minus 6 times 0 squared, and that is equal to 0. Now when x is equal to 4, you have 4 cubed minus 6 times 4 squared. And then you plug that into your calculator. And this is equal to negative 32. And we have negative 7 cubed minus 6 times negative 7 squared. Plug this into your calculator. You get negative 637. Then for f of 7, you have 7 cubed minus 6 times 7 squared. Plug this into your calculator. This is equal to 49. Then next is to compare values. The largest value here will be the maximum. In this case, it is 49. So this is the absolute maximum. And the lowest value, which is negative 337, is the absolute minimum value. Another example. Find the absolute extrema of the function on the given interval. The first step is to make sure that this function is continuous on this closed interval here. And again, since this is just a polynomial function, it is continuous everywhere. So therefore, this is continuous on this closed interval. So then next is to find the critical numbers. To find the critical numbers, we are going to find the derivative of the function. So let's differentiate each term here. The derivative of 2x cubed is 6x squared. And the derivative of negative 3x squared is negative 6x, minus the derivative of 12x is negative 12, and the derivative of 4 is 0. Then you equate the derivative to 0. And next is to factor the expression here. Now we have a common factor, which is 6. So you have x squared minus x minus 2 equal to 0. Furthermore, you can also factor this out. You have x minus 2 times x plus 1 as your factor for this trinomial here. Then you equate each factor to 0. Since this is just a constant, then you can just disregard that because 6 is always equal to 6. Now the only time this will be 0 is when this factor here is 0 or this is equal to 0. So that means we will equate each of that to 0. Oops. X minus 2 is equal to 0 or x plus 1 is equal to 0. Then when x minus 2 is 0, that implies x is equal to 2, or if x plus 1 is 0, that only happens when x is equal to negative 1. Now at this point here, we are going to evaluate the function and also at the endpoints of the closed interval. So we are going to evaluate the function at f of 2, and then f of negative 1, then f of negative 2, and f of 0. So we have 2 times 2 cubed minus 3 times 2 squared minus 12 times 2 plus 4. And then you plug this into your calculator. You get 16. And at f of negative 1, you have 2 negative 1 cubed minus 3 negative 1 squared minus 12 negative 1 plus 4. Plug this into your calculator, you get 11. And similarly, at f of negative 2, when you plug this in, when you plug in negative 2 at x, and then evaluate it using your calculator, you get 0. And at f of 0, you get 4. Now the next step is to compare these values here. The lowest value will be the absolute minimum. So that means 0 at x equals negative 2. You get you get y equal to 0. So this is your absolute, this is the absolute minimum. And the highest value in this case is at x equals 2. So this 16 here is the highest value. That's your absolute maximum. So we say that f has an absolute minimum at x equal to negative 2. And if you're asked for the value, the absolute minimum value is 0. Also, you say f has an absolute maximum at x is equal to 2. And you say that the absolute maximum value is 16.